All right, in this example problem, we're told that a machine gear initially at rest accelerates to a final angular velocity of 6 radians per second over a time period of 6 seconds. We're asked to solve for the constant angular acceleration of the gear during this time, and then the angular displacement of the gear as well. I've listed the 4 kinematic equations for rotational motion on the bottom left of this slide for reference. As always, when solving problems, it's a good idea to list the given information before proceeding. In this case, we're told that the gear is initially at rest, and so I know that the initial angular velocity of the gear will be 0. In other words, the gear is not rotating at the beginning of this time period. We also know that the final angular velocity that we're looking at is going to be 6 radians per second. And we're told that this all happens during a time period of 6 seconds. And we're solving for alpha, the angular acceleration of the gear. Given that I have the initial and final angular velocities and the time, which kinematic equation do you think we should use to solve for alpha, the angular acceleration? If you said this equation, I would agree. Right? We know 3 of the 4 variables in this equation, just leaving us alpha to solve for. I'll go ahead and rearrange this equation for alpha before plugging in any values. I'll begin by subtracting the initial angular velocity, omega initial, from both sides of the equation. Now that I've finished my subtraction and addition, I'll go ahead and divide both sides by t, the coefficient of alpha, to get alpha by itself. All right, now that I've rearranged my equation for alpha, I'll go ahead and plug in the values I was given. When you do, you'll see that alpha, the angular acceleration, is 1 radian per second squared. What this is saying is that every second, the gear is increasing its angular velocity by 1 radian per second. So in other words, 1 radian per second per second. Let's take a look at part B now, the angular displacement of the gear during this time. Please recall that the angular displacement is represented by delta theta. In this case, I have the same set of given information, omega initial, omega final, and time. I also have alpha now that I can use as well. So based on these 4 pieces of information that we have, which kinematic equation do you think we should use for part B? In this case, we have enough information to use any of the 3 remaining kinematic equations to solve for delta theta. I'll go ahead and use the third equation. Substituting in for omega initial, time, and alpha, delta theta becomes 18 radians. Now, if you were curious how many revolutions this was, or in other words, how many times the gear rotated 1 full time, you could convert radians to revolutions if you wanted to. Recall that for each revolution, there are 2 pi radians. So I can do dimensional analysis like this to solve for the number of revolutions. I'll take my 18 radians, and I'll multiply it by my conversion factor. This will give me about 2.9, roughly 3 rotations. All right, let's take a look at another example problem.